I had my first summer job as a student, undergraduate student, down here in Baja. You've probably all heard of Gordon Gastel, who mapped most of the Baja California del Norte. And so every summer he would have a team of students. I had only a few classes in geology, but I came from geophysics and astronomy, and so he knew I could operate a gravity meter. So that's what I did for my first summer job. I spent the whole summer, all 3 months, going over every possible road in northern Baja California, taking gravity measurements. So my history goes way back, and at that time, one of the students who worked mostly in geology was Francisco Suarez. So I knew Francisco for 50 years. And it turns out that when I was preparing this talk, I realized that there's another connection, because when it came time for me to do my PhD work at Stanford, my advisor, Alan Cox, gave me some rocks that the U.S. Geological Survey had made measurements on from what was called the experimental mohole. Now that's before a lot of your time, but before the ocean drilling project got started, the first effort to drill a deep hole in the deep ocean was in this between Vizcaino Peninsula and Guadalupe Island. And they only went down 600 meters, and then they hit a basalt, probably a sill. But the Geologic Survey then got cores of that rock, and those were the cores that my advisor gave me to start my research on. And that led into then coming back down to Scripps to get samples of pillow basalt to continue my research. So both the beginning of my undergraduate career and the beginning of my research as a grad student had its origins here in Mexico. So it's good for me to be back, and Jorge Ledesma was taking classes at State shortly after I came down from the survey and started on the faculty, came back to San Diego State. So the motivation for this talk is that a lot of my friends, people my age, are dying, and so most of you, all you know is plate tectonics. You were never exposed to the old theories of geosynclines and things like that. And so when I was an undergraduate, my last year in 1966, the professor who seduced me, who attracted me from physics and astronomy into geology, I had him for a class, and he said, well, there's some geologists, particularly in the southern hemisphere, South America and South Africa, who think that Alfred Wegener's idea of continents drifting to open the Atlantic Ocean is true. He said, but it's a stupid idea. And that was the word he used, stupid. Okay, well, a year later, I was up at Stanford in grad school, and guess what? The assignment in my advanced structure class was Continental Drift, and then Alan Cox left the survey and came on the faculty at Stanford in the geophysics department, and so I picked him as my advisor, and I ended up working on what turned out to be the rocks that cause the magnetic anomalies that are the key to seafloor spreading and plate tectonics. So I'm one of the few people who know what it was like then, went through the revolution, participated in it, and now in the new, you have paradigm? In Espanol, paradigma, or paradigma, yeah, the nueva paradigma, right? And so anyhow, I thought, well, you know, you maybe know all of this, but it might be nice to hear from somebody who went through this process and to know the details of what really happened and how things really were proven or disproven. Okay. Okay, so this is in 6 parts. My own experiences during the 60s. Alfred Wegener, good idea, but the wrong mechanism. Okay, and then how the combination of the marine magnetic anomalies along with the geomagnetic reversal timescale, which my advisor was one of the main scientists to work that out, how that combination proved seafloor spreading. Okay, and then how then people advance from seafloor spreading to plate tectonics. So you want to be very careful, and I'm sorry I can't say this in Spanish, but continental drift is not the same thing as seafloor spreading, is not the same thing as plate tectonics. Okay, people tend to use those words interchangeably, but that's very loose speaking. If you want to be strict about it, each one of those terms has its own set of ideas, which are very different and in some cases self-contradictory. So, okay, and then another person that I've known since she was a grad student at Scripps and I was up at Stanford is Tanya Atwater. So I've known Tanya. They invited me down to give a talk at Scripps when I was doing my research. And so Tanya had a party for me after my talk. And so I've known Tanya Atwater for 50 years. And she was the first person to say, okay, you know, you're working out all these tectonics of the seafloor and the ages of the seafloor. But is there any connection between what goes on the seafloor and what goes on the continent, between marine geology and continental geology? And she was the first person, to my knowledge, to make that connection, to bring the offshore knowledge to onshore problems. Right? Okay, and then taking off from that, coming down to our own area in preparation for the field trip that SDAG is going to have in October. What's the story behind the geology that you can't see, all the geology that's underwater off of our coast? Okay, so it's too bad, 30 meters of water and you don't see anything, right? That's why dolphins and whales have such good sonar. So. Okay, so my first summer job, I told you about that. Oh, and then I have a funny thing. Okay, that's me, summer of '64. Somewhere in northern Baja. This has been so long ago, I don't remember where it was. Some of you may recognize the terrain or territory or the vegetation, but you know, it's some deserted place, right? With cactus and that's the old gravity meter that we had at the time. So, okay, gravity is heavy work. So, so there I am. We camped out, of course. There were no facilities and we didn't have any money. So we camped all the time. We just had cots. And you can see I had a beard then because we were down there for 3 months and there was no hot water. There was no electricity in most places we were at. And so I couldn't shave and I decided to let my beard grow. Well, it turns out that I looked a lot like Fidel Castro. Okay, and so you'll see the Jeep that we had in the next picture, but when we'd drive down little towns like El Rosario, which were much smaller than they are now, people would look at me and they'd go, Fidel, hey Fidel, and I'd go, Yankee, go home. So anyhow, so that's our, and you can't read it, but it says, Estudio Geológico, and then it says, I think, UABC on it, right, Jorge? So that was sort of to show the people that we met that, you know, we were legitimate scientists and we had a Mexican connection, okay? And so, okay, and this is what happens, and I'm sure a lot of you can identify with this. This is my bedroom. Okay, well, my computer is just off to the right. My bed is behind this picture, and I find it very helpful when I'm writing a paper or preparing a talk to spread stuff out on my bed so I can just see things all at once. And it's easier than putting it on the floor or the dining table, right? So anyhow, so that's just the floor part of my bedroom. Okay, so that's probably a lot of you, especially people who've written papers, can identify with that creative mess. Okay. Okay, so now let's talk about good old Alfred. He was basically, he majored in astronomy and meteorology. He had a checkered career from one German university to another, but he was a mountain climber, and his passion was exploring Greenland, which is where he died, and I'll tell you that later. So in any case, in the 1950 into the 20s, he published a series of articles on what he coined the term Continental Drift, and he just noticed the nice jigsaw fit of you just close up the Atlantic and how Brazil fits into Africa and North America fits into Northwest Africa and Canada fits into Europe. He wasn't the first person. Other people noticed that fit, but he really went into it much more scientifically than anybody had before him. But the problem was that he wanted the continents to drift or to move apart. And so you'll see that it was a great idea, but his mechanism was totally wrong. So, okay, so there's Alfred in his under ice hut in Greenland. There he is again. That's the last picture taken of him with his Inuit guide. He and his guide set off on a trek in Greenland to visit one of their bases, and they never returned. And so some months later, they found his frozen body. And so he's the father of continental drift, and in a way, the father of plate tectonics. Okay, so in the lower right is his drawing from his publication. And so you could see how nicely he fit things together. In fact, the only real difference between and he coined the word Pangea. Pan from Greek, all, Gea for earth. So he's the one who used that word, okay, who coined it. And you see a modern view of Pangea, which as far as the Gondwana continents go is exactly the way he had it. The only real difference is that we now know that Asia was sort of off apart from this main mass of Pangea with a sea called the Tethys Sea. Okay, so now the problem with continental drift, okay? And that is the geophysicists, especially the seismologists, knew that continental crust was about 7 times thicker than oceanic crust, that mountains have more or less roots, and so they thought, look, you know, it's impossible for these thick continental blocks to plow their way through across the oceans, through the oceanic crust and mantle. All right. And there's no force known. He thought, well, maybe it has something to do with certain oscillations of the earth and stuff, but a British mathematician proved that there's not nearly enough force involved to move continents. Okay, so this is sort of an exaggerated view of this mountain with a really deep crust, deep root, but you can see how much thicker continental crust is than oceanic. The typical thickness, this is taken from a textbook. I don't agree with some of those things, but in any case, the oceanic crust typically is about 7 kilometers thick. The average continental crust is 40 kilometers thick. So there really is like a 5-to-1, 6-to-1 ratio between the thicknesses. So you can just imagine what would happen if you took that chunk of continental crust and tried, say, moving it to the left. What would happen on the right side? You'd leave a great big hole, right? What would happen on the left side? Wouldn't you just compress the oceanic crust and there'd be giant slabs of oceanic crust being thrust up into the air from the seafloor? Well, oceanographers knew there weren't any holes on one side of South America, and on the west side of South America, the seafloor looked just fine. All right. So anyhow, that took care of continental drift. All right. Okay, so no force known is great enough to move them, and then you have all this oceanic crustal deformation which is not observed. So, how to get around this? Okay, well, the way they got around it started with a very fortunate coincidence in time in the 60s between the marine geophysicists who were out doing their surveys of the ocean, usually focusing on the seismic surveys, the bathymetry. But some places, especially Lamont, which is part of Columbia University in New York, towed magnetometers along with the seismic gear. And so they were finding all these wiggles. I don't know, in Spanish, you could say something like líneas ondadas or something like that. How do, huh?
Onduladas. Onduladas.
Onduladas?
Líneas onduladas. Líneas onduladas.
Oh, líneas onduladas. Onduladas. Yeah, so we just, in English, we say squiggles or wiggles. Okay, so they were finding these wiggles all over the place, but they didn't know what caused them. All right, and totally separate now, the people on land, two groups, one at the lab that I worked at the survey in Menlo Park, south of San Francisco, another group in Australia were going out and collecting usually basalt samples on land, anywhere they could find recent basalts, measuring their direction of magnetization and using a new technique at that time, potassium argon, to measure the age. And it turned out that, well, I'll show you in the next slide. Okay, so the first part is learning about the Earth's magnetic field history. The history of polarities, different polarities or reversals, okay? And they could only go back 4 million years because potassium argon was too inaccurate to go back any further than that, to get the resolution you needed, because there have been lots of reversals in the last 4 million years. Okay, so here's the typical ski showing how, you know, the magnetic field is created in the core. Essentially, by the time you get to the surface is a dipolar field, just as if there were a big bar magnet buried in the center, except that the Earth's bar magnet can flip, okay, and it does that. In the Cenozoic, it's flipped on average, I think, every 200,000 years. So in any case, the flipping of the field itself was a controversial idea. People started discovering rocks in the early 1900s that were, you know, had the magnetic direction, instead of being north, south. And so for a long time, people said that's impossible, right? But it turned, and so the way it was proved is by the people at my lab and the Australians going all over the world, collecting all these oriented cores and showing that the field was either normal or reversed at the same time everywhere in the world. And so that proved that the Earth's field does reverse. Okay, so this is my advisor from Stanford. This was when he was working at the survey. So in those days, they had these chainsaws that the mechanic in the USGS lab in Menlo Park, the machinist, converted this chainsaw into rock drills. And down at the bottom, you see what the core. These cores are like 2.5 centimeters long and 2.5 centimeters in diameter. And typically, with one of those things, if it's a basalt, you could core 10, 15 centimeters into the rock, pull out the long core. The white line, the yellow line right here is orientation line. So when you get it back to the lab, you know, and you take the orientation of the core before you pull it out of the rock. So in any case, this is how they were out all over the world sampling younger basalts, less than 4 million years old. Okay, and then the way it worked, this is an article by Alan Cox and the other people in that lab in '67 now, okay? They made a plot. They had time on the vertical axis, and they took all the flows that were normal and plotted them on the left of that center line, and all the rocks that had reverse magnetization to the right. And so you can see there were times when the Earth's field was reversed and times when it was normal. And the times are random. It turns out that sometimes the field will maintain its polarity for as short as 20,000 years. And there's a time in the middle of the Cretaceous where it was normal for 40 million. So it's totally a random process, these fields, which is good because they thought at first it was periodic. Well, it's not, it's random, and so you get a barcode. So you know, that's very useful because every place on the seafloor of every age has its own barcode associated with it. So you can sail over the oceans just towing a magnetometer, and if you can identify the squiggles, the ondas, right? You know how old the seafloor is. You don't even need to go down to the bottom anymore. Of course, they did it first, but not anymore. Right? Okay, so this now is from Alan Cox's book. This is really a good book. He published this in '73. It's a compendium. It consists of all the important papers that were published in the '60s that led up to this revolution. And so if you ever want to sit down and just go through and see what famous people like Fred Vine, who was the first person to make the connection between magnetic anomalies and seafloor spreading. There's articles on the seismology of plates. It's a very, it's old material, but historically and scientifically, it's very valuable to see the path of such an important scientific revolution. So you can see up at the top, in the early days, that it looked like the field was normal from 0 to 1 million years, and then reversed. The black is normal, white is reversed, and then for the next million years it was reversed, and then maybe for the next million years it was normal. Well, eventually, as they got more and more rocks, and that chart that you just saw got filled in with more and more dots, either on the normal side or on the reverse side, look how complicated. Now you can see the barcode on the bottom line, okay? And so what they did is they named this most recent normal time the Bruns normal, after a famous French paleomag person. And then this long stretch of mostly reverse, but not entirely, they called the Matayama, after a Japanese paleomag person. And then Gauss, the famous German mathematician, and then Gilbert, a British scientist. So what they did is they divided this barcode up into these intervals that they called epochs. Well, it turns out the stratigraphers had already used the word epoch, like Miocene, Pliocene, Oligocene. Those are all epochs, right? And so they said, wait a minute, we already reserved the word epoch for time periods based on paleontology. You can't use that word. So now the word is chron. So in any modern literature, and now instead of putting people's names, because they have so many crons and subcrons, they just number them. Okay. So these poor guys, those 4 famous scientists, don't show up anymore. Okay. So in any case, now the linear magnetic anomalies. All right. Well, the people at Scripps found these magnetic anomalies and mapped them offshore of Oregon and Washington. And what they did, the way why they're called linear, is each ship track would have its squiggly lines, its own dust, right? And then, but they would notice that, and the ship lines were only like 5 kilometers apart, they could correlate the peaks on one set of ondas with the peaks on the one to the north and south. And so they just took and said, okay, let's take and color with a black pen through all the peaks, all the positive anomalies, and that ended up then producing a map that had a bunch of horizontal lines or stripes. So you'll hear that term, the magnetic stripes, okay, or the linear magnetic anomalies. That's the basis for that term. All right. Okay, so now, how are these recorded, these anomalies? All right, here is this is a textbook example. This is 0 time, and we're going out through, this is Bruns, this is Matayama, this is Gauss, time. Okay, so we're going back 3 or 4 million years here in this textbook example, but it's an accurate curve, all right? And beneath it, it shows what's causing these hot magnetic highs and lows, because when the magma comes up at a spreading center and flows out, especially the pillows, and I'll talk about those in a second. That's the work that I did. Thanks, Margarita. Well, I'll say it right now. The pillows are, because they cool so fast, the magnetite grains or titanomagnetite grains are what are called single domain or pseudo single domain. So the pillow basalts are 10 times more magnetic than if that same basaltic flow had flowed out here on land. Okay, so it only takes a half a kilometer or so of pillows to generate these magnetic anomalies. All right. So in any case, so the lava comes up, it creates dikes and stuff, as you'll see, but the pillows flow out. They're pretty much centered there in the center valley of the spreading center. And then as the 2 sides move away, this is totally like a double-headed tape recorder, that as the Earth's magnetic field reverses back and forth, it produces strips of oceanic crust that are normal and reversely magnetized. Okay, so when the ship goes over a section of crust that's normally magnetized, by normally mean like now, okay, then the field, the magnetic field associated with those pillows down in the bottom of the ocean, and to a certain extent the dikes, it reinforces the current field and the magnetometer reads high. When you go over a strip that's reversely magnetized, that magnetic field tends to cancel out the Earth's field, and so you have a magnetic low. Right. So that's how seafloor spreading centers, thanks to, how they record these squiggly lines. All right. Okay, and you probably all know this, the typical cross-section of oceanic crust with the pillow lava on top where it hits the seawater. Lava, when basaltic lava hits water, it doesn't have to be salt water, fresh water will do the same thing. It forms these lumpy, bumpy forms that are called pillows. And they're range in size from the size of a watermelon to a small car. But they're fed by these dikes that come up. And then those dikes in turn are fed by a magma chamber. Okay, here's a picture of seafloor pillows, young with a dusting of marine sediments. The organic oozes. You get very far away from a spreading center and you don't see the pillows anymore because they're buried under meters and then kilometers of sediment, mostly organic or in some cases clays. Okay, now here is a real profile. Okay, so the top line is the real magnetic profile that the people at Lamont recorded across the South Pacific from the Mid-Atlantic Ridge, MAR, okay, all the way over almost to the coast of Brazil. So this is what I mean by the ondas, líneas ondadas, okay. So what the people at Lamont did is they said, okay, we're finding this same pattern all over the place, so let's number them. Okay, so let's start at the spreading center and we'll call that positive magnet, that high, 1. Okay, and 2, 3, 4, 5, all the way out the anomaly 31, which is like 80 million years. All right, so this profile, since they found from all their magnetic profiles over the world's oceans, seemed to have the most constant spreading rate. They didn't know. Nobody knew the age of the seafloor at this time. In fact, that's part of the revolution. In the 60s, most geologists thought that the seafloors had always been there and that they were older than the continents. Totally the reverse of what we think now. That was part of the motivation for drilling that mohole off of Guadalupe Island. They figure, well, if the seafloor has been there for 4 billion years, we should be able to drill down and not only see Cenozoic sediments, but Mesozoic and Paleozoic and Proterozoic, right? Well, wrong, right? Okay, so, but this profile became the standard profile that everybody like Tanya used. And so when oceanographers went out and measured the marine magnetic anomalies off our coast, they would try to match them to what you see here. And assuming a constant spreading rate, then say, okay, the seafloor at this place is X millions of years old. Okay, well, in the early days of the plate tectonic revolution, when the experimental mohole failed, huge cost overrun, they initiated what was called the deep sea drilling project. And instead of drilling one deep hole to try to reach the mantle, they drilled shallower holes all over the world's oceans, starting first right along this section of the Atlantic and going down through the sediments. And you can't date submarine basalts very well, but you can at least, the paleontologists can look at the forams and the radiolarians at the bottom of the hole, just the rocks, the sediments deposited on top of the basalts, and find out how old they are. And it turned out, remarkably, that the age of the Atlantic seafloor was almost exactly what the people at Lamont had predicted on the assumption of constant spreading. Okay, that it wasn't Precambrian, you know, it was Cretaceous at the oldest. All right. So in any case, so now people still use those numbers. Sometimes they'll put the word cron in front of it. But that's where the numbering the anomalies started in 1968, and that was the year when things broke wide open. And I was at the meeting, it was the American Geophysical Union meeting in San Francisco in December of '68, when the people from Lamont showed this profile and profiles they had taken from all over the world, and it proved seafloor spreading. And here's how it did, okay? Notice you have this barcode down here. So what they did is said, okay, here's anomaly 13, this is a high, so let's put in a block of positively magnetized crust, all right? And so this then is the model, and then they ran that through a computer to generate these curves. Okay, now let me go to a more close-up and you'll see how closely the observed squiggles match the theoretical ones. Oh, I thought I had a close-up. Well, I guess I don't, okay? So in any case, you can look. This is modeled, okay? This is observed, and you can see, you know, that, well, in fact, you can see how symmetrical the anomalies are. And so then they brought in the more refined time scale to put in, you know, at least for the last 4 million years, what we know the reversals have been. And so I think in the next slide, yeah, so that basically the three properties of the linear magnetic anomalies that proved to almost everybody's satisfaction by 1968, okay, that the seafloor, that ridges, oceanic ridges and rises really were spreading centers, okay, were the following things. One, bilateral symmetry. You could say the same pattern on one side of the spreading center as on the other. Okay, and that same pattern of highs and lows were true for every spreading center. Right. And then finally, they perfectly matched the geomagnetic reversal timescale, at least as it was known to 4 million years ago. Okay, so then people could turn the whole process around and say, okay, potassium argon isn't very good for rocks older than 4. Why don't we just use that squiggle pattern to define when the Earth's field was normal and when it was reversed. So first the horse pulled the cart, and then the cart pulled the horse. And so it was perfect. And this all happened in about 1968. And in my experience, we sat there, and after these talks, we knew, you know, this idea of seafloor spreading that had been so controversial, we knew the controversy was over, that it was true, right? And that was an amazing meeting. So,
do you know how many people there was
at that meeting?
At that session?
They held them in great big rooms. There were hundreds. There were hundreds. Now, I've had sabbaticals in different countries, France, Russia, and I found, like when I was in Russia, the older geologists, this is 1993, still didn't believe it. So it really came down to a generational gap. People like me who was, you know, in their 20s or early 30s, boy, we hopped right on it. But a lot of older geologists, they had grown up with the old way, the fixed Earth, where things can move up and down, but they don't move laterally, okay? They really clung on to that, and it's interesting psychology, right? The psychology of science, right? So you sort of believe what you were taught, except for people like me, right? Los perros bravos, right? Okay, so now, okay, so the sea is going out, but then what happens to all the stuff that's produced at the spreading centers? Well, one geologist, very famous, he's either, I think, Australian, said, well, I think the Earth is getting bigger. Well, that certainly would accommodate more crust, right, if you could expand the size of the Earth. Well, hold on. Okay. Okay, so it turned out, and again, this is so coincidental, all these, the advances in geomagnetic field reversals, detailed studies of linear magnetic anomalies, and more sophisticated seismology, seismologists discovered that there are 2 additional layers in the crust and upper mantle that had gone undetected. Remember, Mohorovičić discovered the Moho when in 1917 or something, right? Well, it turns out that's not all there is to the upper part of the, it's not just Moho and then going all the way down to the core. So they discovered 2 more layers. And so now look at the difference in this model. First off, it doesn't have the deep mountain roots, but the key thing in this diagram, okay, is that the upper 100 kilometers, okay, they found that the seismic properties, that the upper 100 kilometers of both the ocean, underneath the oceanic crust and the continental crust were really strong and pretty rigid, whereas it used to be called the low velocity zone, especially with S waves, they found that there was a layer from 100 down to at least 200, maybe 300, that could even possibly be partially molten, 5% melt and the rest crystals. And so it mechanically is much weaker than the lithosphere, and so it was called the asthenosphere. All right? And that solved it, right? It's not just the continents that plow their way through the oceanic crust, it's the whole lithosphere that moves, and it has a fairly flat bottom, and it's sitting on top of this gushy layer that makes it even easier for that upper 100 kilometers to move. So that's the refinement that broke the knot. In English, we say Gordian knot. It comes from a Greek thing about, you know, there was a knot and some Greek person, God, came along and just cut the knot with his sword, and that solved the problem, right? And so, okay, so this is the first example that I've been able to find of people using those terms, and this came out in an article published by Lamont seismologists now, not marine oceanographer types, where they use the word lithosphere and asthenosphere. And so now you can see, and in this article they showed the various ways that pieces of the lithosphere could subduct. Here's the spreading center. There are transform faults, right? So, you know, in '68, this came out and they said, look, this now is the real story. So the Earth isn't expanding. What's produced at the spreading centers is just being consumed in the subduction zones. How long do I have? When should I stop?
15 minutes.
Huh? 15 minutes? 15? Okay. Yeah, because I want to leave time for questions. And, okay. I may rush through some of this last part, but. Okay, let's talk about what Tanya Atwater, she contributed. That's her. Okay, and you can see she has a very sly smile, right? She's one of the most famous female geologists in the world, right? I mean, what she did in 1970 was revolutionary. And so she never had to do anything the rest of her life, just that one article in Bulletin of GSA in 1970, and she would have been famous for the rest of her life. She started off at MIT, and then after Scripps, she got a job at MIT, she and her husband, Peter Molnar. Peter stayed there, they got divorced, she moved to UC Santa Barbara, and that's where she was until a few years ago when she retired. Okay, so. Okay, now this is, you all know this, right? Well, people didn't know this pre-plate tectonics and pre-Tanya. She took all the magnetic anomaly profiles she could find at Scripps, along with Bill Menard, who had been saving them for years, not really knowing what they said, what value did they have, right? And so now you know the oceanic tectonics, the plates in the Pacific Ocean, right? The biggest, by far, the biggest plate in the world is the Pacific Plate, right? It occupies almost the entire North Pacific, right? And then your favorite place, a little tiny platelet down here called the Rivera Plate, right at the Gulf of the mouth of the Gulf. But then most of Mexico and Central America is being subducted by the Cocos Plate, right? So you guys probably all know that very well. And then once you get down into South America, from Bolivia or whatever south, almost to Patagonia, that part of South America is being subducted by the Nazca Plate. But these plates, the Nazca, the Cocos, and then the plates diving down beneath Northern California, Oregon, and Washington, those are all just leftover pieces of one much larger plate. And so what Tanya did is say, hey, you know, most of the Pacific Ocean is this one plate, but as far as anybody knows, its spreading centers, as much is produced on one side, there's a symmetry, as on the other. There's a few places where a little more is produced on one side than the other, but usually it's the same. Therefore, there must have been subduction of the other, the missing half, largely missing with the exception of a few pieces, but missing off of the two Californias, okay, where the Pacific Plate now touches the North American Plate, okay, there must have been a patch of seafloor as big as practically North America subducted. All right, so that was the big contribution that she made just by studying the magnetic anomalies. Okay, so here are the magnetic anomalies. Here are those lines that I told you where you just draw lines through adjacent peaks. Okay, these, you notice they're numbered. Okay, and I darkened in anomaly 13. That's going back to the old Lamont numbering system. Okay, and you can see how zigzaggedy the spreading center was. It's offset by all of these fracture zones, which are transform faults, right? So guess what part of the Farallon Plate, or what part of the Pacific Plate touched North America first? Well, it's going to be this part right here, right, between these two fracture zones. And I think I do have a, yes. Okay, so it's close up. Okay, so look, this part, here's the Mendocino fracture zone, Pioneer, Murray. Okay, so here's the spreading center back, you know, some time ago. Okay, and so notice that the anomalies are canted or tilted to one side, and there's these northwest southeast lines called pseudo faults, which result when a plate changes the direction of spreading. Okay, they're called pseudo because they're not really faults, but you can see what's happening here. As the spreading center got closer to the continent and the space, the spreading trench gap narrowed, that section of Farallon Plate started getting screwed up, and that part of the Pacific Plate started getting distorted too. So what she did then is she said, okay, let's assume that none of the Pacific Plate has been subducted, only the Farallon Plate. And let's look at the youngest anomaly, like anomaly 6 here, okay? And we'll just look at the youngest anomaly off the coast, and we'll say, okay, that's when the contact was made, okay? So she came up with this picture that you probably all know that's so famous, the beginning of every textbook, right? Here's 40 million years ago, here's Pacific Plate, total Farallon Plate off of off of North America. But at 30 million years ago, in the vicinity of Los Angeles, the Pacific Plate first touched, made contact with the North American, and then that point of contact turned into a line. And that line, of course, now is the San Andreas Fault. So another view of this is just a map view. Again, 30 million years ago. The real contact probably was closer to 26. And then here's the contact with, you know, right laterals, strike slip, transform. And then you had two what are called triple junctions, the Rivera triple junction and the Mendocino. The Mendocino migrated up the coast. The Rivera migrated down the coast to where it is now off of the mouth of the Gulf. And then, of course, the Mendocino triple junction is up at Cape Mendocino in Northern California. So you had this period of time then where the Pacific Plate was rubbing against the North American plate and causing all sorts of, you know, transform motion somewhere up in the continental borderland or maybe even in air up on land. Okay, I'm going to go. Oh, and then of course she pointed out, and this is great, right? She wasn't the first person, but here are the anomalies in the mouth of the Gulf, okay? And so you say, okay, well, it's about 250 kilometers of oceanic crust that have been created since anomaly 3, which is 5 million years old. A neat rule of thumb for these anomalies is that most of them, the age is twice the number. Sometimes it's 3 times the number, but in general, if you see an anomaly number and you want to know how old is the oceanic crust, just double the number. Right? So that basically gives you an average rate of, on the San Andreas and of the opening of the Gulf, of 50 millimeters per year. Okay, now this is beautiful. See, because now what I was telling you, you can take all those ship tracks, you can correlate them with the standard curves from Lamont, and then now they've upgraded it and extended them. And so now you can take and you can map the ages of the seafloor in the Pacific. Okay, and so I label these. So you can see all of this seafloor is created in Eocene time. This seafloor in here, Upper Cretaceous, Middle Cretaceous, Lower Cretaceous, and then the oldest seafloor in the North Pacific and probably the world is offshore of Japan, Upper Cretaceous. So I mean, that's a beautiful map, you know, just showing you the age of the seafloor. And of course, continental geology, right, is so much more complicated than seafloor. Okay, I'm going to show you something, a very nice. Okay, I'm going to finish off talking about current ideas for the formation of the enlarged margin offshore of the two Californians. Okay, extending, that enlarged extended region extends from Santa Barbara on the north down to the Vizcaino Peninsula. To the north and south, the continental margins are undisturbed pretty much and are narrow. Okay, well, it's 300 kilometers or so off of San Diego until you get to the Patton Escarpment, and it's like 250 west of here. Okay, so we have a very tectonically disturbed and disrupted continental margin from Santa Barbara to the Vizcaino. What's the modern theory for how did that happen? Okay, so I'm going to very quickly try to end this. Okay, the key discovery was when they looked closely at the linear magnetic anomalies near the coast, okay, they found, see this line of dots, this is the old Farallon spreading center. So here's anomaly 6, here are the 6A, B, and C. So this part either didn't get subducted, that part of the Farallon plate, or it got subducted and pulled back out. All right. So that's the key thought here now. Okay, and it turns out this is happening off of your coast too. Here's Ensenada, the Vizcaino Peninsula is down here. Those lines of dots, in fact, now you can really see it. Look at this between the Guadalupe and the Shirley fracture zones. Here you have a dead spreading center. This is Farallon plate, this is Pacific plate, and look, 5B, 5B, 5C, 5C. So it's totally obvious that here's a big chunk of Farallon plate that either didn't get subducted, or if it did, it got pulled back out. And Joanne Stock at Caltech uses this as a reason why you have the proto-Gulf that's spreading in the Gulf of California, or at least an inland sea, started 12, 13 million years ago, not just 5. All right. Okay, well, I'm going to very quickly go through all. Okay, I'll finish with this really. Tanya, go on her website. It's just Atwater, you know, she's at, I think it's still Atwater at ucsb.edu. Okay, and she has all these great movies. All right, and so this is the movie that applies, this is her model for the formation, it's a movie showing how she thinks this widening of the continental borderland and the rotation of the western transverse ranges by 90 degrees, how it looks, at least in a map view. All right. So let me see now how to do this. Okay, I want to engage this slide. I don't want to go forward or back. What do I do to engage the, maybe just press enter or something? Oh, you got it. Okay. Now watch this. This is really cool. SB is Santa Barbara. Those are the western transverse ranges. There's the Vizcaino Peninsula. See, and then at 5 million years, the San Andreas kicks in and everything starts moving north. But between 20 and 5, in fact, let's, you just pressed enter, Margarita? Or,
you want to see it again?
yes. No, because I mean, this is so good. People, you need to see this 5 times at least. But, okay, what are you pressing? Oh, you're using the keypad. Okay, now watch. San Francisco, Santa Barbara, San Diego, Vizcaino. Okay, notice the transverse ranges rotate 90 degrees clockwise. The outer part of the continental borderland, let's do it again, please. The outer part of the continental borderland is just transported north. So it still has the 4 arc sediments deposited probably on the Franciscan Formation. But the inner part, now watch the inner part of the continental borderland. This, look at this part in here, okay? All the dredging and seismic studies tend to suggest that that whole, see, this area has been doubled. The width of the continental margin has been doubled. Well, it's doubled, one, by taking the outer part and moving it to the north. Well, that doesn't double it. What really doubles it is having the outer part of the old margin pull away from the shoreline. Yeah, let's do it again. Pull away from the shoreline, and that happened on top of the old Farallon subduction zone. Watch. This area in here now, okay? As far as people can tell from dredging and coring and stuff like that, this whole area here now has Miocene sediments and basalts on top of schist. And so what happens is when the Farallon plate went down, it had a very low subduction angle. It just went along the bottom of the crust and apparently even eroded some of the lower crust. And then and all those sediments from the ocean were carried down so deep they were metamorphosed into green schist, blue schist, in some cases even amphibolite grade metamorphics. All right. And so that's what we see offshore here, and those same schists have been correlated to the ones on the other side of the San Andreas in the Oricopia Mountains, and up in LA to the Pelona schist. So this is a really different way of thinking about what the Farallon, what subduction is not as simple, the bottom line here, for our area. Subduction is not a simple process. Subduction can erode material as it rubs along the base of the crust if it's shallow. It can deposit material. It'll metamorphose oceanic sediments. And it looks like that when those spreading centers that you saw by the lines of dots suture together, when the lava's cooled down and those pieces of the Farallon plate really got glued to the Pacific plate, the Pacific plate is moving to the northwest. And to the extent that those last little pieces of Farallon plate got attached to the Pacific plate, they were drugged to the northwest, which raises the possibility that what had been subducted is now being pulled back out. Okay, and so that's the story for our continental borderline, and that's it. And so,